Welcome to the deep dive. We're here to, cut through the noise and get straight to those aha moments hidden in all the information out there.
Exactly. Making sense of the complex stuff.
And today, we'll look around you. Solar panels are just everywhere now, aren't they?
Uh-huh.
On rooftops, out in huge fields, just quietly doing their thing, soaking up sunlight. It feels like such a normal part of our energy world now.
It really does. It's transformative.
But have you ever really, stopped to think about the science behind it? Not just the big panels, but the tiny, intricate stuff that makes them work better and better.
Yeah, it's not just about scale. There's this relentless push deep down at the microscopic level. It's all physics and material science.
Constantly pushing the limits of what you can do with light.
Precisely.
So today, we're doing one of our deep dives into exactly that. We're taking one specific, quite technical document as a recent patent application, and we're going to try and pull out the key insights for you.
Think of it as a shortcut. We'll do the heavy lifting of wading through the jargon.
Yeah, giving you a clearer picture of the kind of breakthroughs happening right now in solar tech.
And this one comes from a real giant in the industry, LONGi Solar Technology.
Okay, LONGi. So before we dive into the patent itself, maybe just a word on them. Why does it matter that this innovation is coming from LONGi?
Right. Well, LONGi, they're based in Xi'an, China. That's LONGi Solar Technology, Jianco, Ltd., the official applicant here. And they are consistently ranked as one of the world's largest solar companies.
A major player, then.
Absolutely. Especially known for their leadership in monocrystalline silicon wafers and modules. That's the high-efficiency stuff, the foundation for a lot of the best panels.
So when they file a patent for an improvement, it signals something significant.
Exactly. It tells you this isn't just some fringe idea. It's coming from a company with massive R&D resources, a huge market share, deeply invested in pushing efficiency. It reflects their strategic direction.
Makes sense. And it's not just one person's idea in a lab coat, right? There's a team involved.
Oh, definitely. The inventors listed here are Zhangwei Deng, Mingsun Bai, Hui Ali, Hubo Zhu, and Phelan Pian. It really highlights that modern R&D, especially in areas like this, it's collaborative.
Teams of specialists pooling their knowledge.
Precisely. And looking at a patent application like this gives us a kind of sneak peek into their R&D pipeline. What problems do they focus on solving right now?
And the document itself, this specific patent application, it has a bit of a history, doesn't it? It's not just brand new.
Right. That's another interesting layer. The document number is US 2250221086A1, published July 3, 2025.
Okay.
But the U.S. application was actually filed back on March 17, 2025. And crucially, it's listed as a continuation of an earlier international application.
A continuation, meaning it builds on previous work.
Exactly. It links back to a PCT application that's Patent Cooperation Treaty number PCTCN 224122489, filed September 29, 2024.
So we're already seeing this progression over time?
Uh-huh. And it goes back even further. It claims foreign priority based on a Chinese patent application, 233113579.6, filed way back on October 18th, 2023.
Wow. So this idea has been in development, refinement for a couple of years at least.
Yes. It really underscores that innovation in solar isn't always about, one giant leap. It's often this steady, iterative process, constant refinement.
Finding ways to squeeze out a bit more efficiency, fix a small problem based on ongoing research.
Exactly. This patent isn't just an isolated invention. It's part of LONGi's ongoing strategy, their portfolio of improvements to stay ahead. It shows sustained commitment.
Okay, let's unpack this then. What exactly is this patent trying to achieve? We know solar cells convert light to electricity, the photoelectric effect, right?
Right. The basics.
But this patent focuses on a specific type, TOPCon cells.
Yes, TOTCon. That stands for tunnel oxide passivated contact. And you're right, these are already known for being very, very efficient.
So what makes them so good in the first place?
Well, the key is that tunnel oxide passivated contact layer. It's a really clever bit of engineering. It uses an incredibly thin layer, the tunnel oxide layer, that electrons can actually quantum tunnel through.
Tunnel through, like magic.
Well, quantum mechanics magic, maybe. But the point is, this layer is very selective. It lets the useful electrons pass through easily, but it acts as a barrier to other processes that cause energy loss.
Okay.
Specifically, it dramatically reduces something called carrier recombination.
Right, you mentioned that carrier recombination. Can you break that down a bit?
Sure. So sunlight hits the silicon and it knocks electrons loose, creating electron-hole pairs. These are your carriers that carry the charge.
Yeah.
Now, you want these carriers to flow into your circuit to make electricity.
Makes sense.
But sometimes the electron finds a hole and just falls back into it, neutralizing the charge before it can be collected. That's recombination. It's lost energy.
Like spilling water before it gets to the bucket.
Exactly. The top econ structure, particularly that tunnel oxide layer, is really good at preventing this spillage right near the contacts, where it's often a big problem. It improves carrier collection, getting more electrons into the bucket, basically.
Okay, so Topicon is already pretty advanced at stopping these losses. What's the problem this specific patent is trying to solve then? Where's the room for improvement?
That's a great question because, even with top econ, it's not perfect. Engineers are always chasing those extra fractions of a percent in efficiency.
Right.
The challenges that remain often relate to optimizing carrier transmission efficiency. That means once you've collected the carriers, how easily and quickly can they move through the various layers to the electrodes?
Minimizing resistance along the way.
Exactly.
Yeah.
And also minimizing any wasted energy, like light getting absorbed in layers where it doesn't generate electricity, just heats things up. So the goal is always maximizing the light to useful electricity conversion. This patent introduces a specific structural tweak to tackle those remaining bottlenecks.
Okay, now we're getting into the nitty-gritty, the layers, the materials. This is where the innovation really lies, right? Can you walk us through it? Maybe skip the specific numbers from the patent diagrams, but focus on what each part does.
Absolutely. Let's build it up. At the base, you have the semiconductor substrate. Think of that as the main stage, usually silicon. This is where sunlight first interacts and frees those electrons. It has a front side for light and a back side.
Got it. The foundation.
Then on at least one surface of this substrate, they apply this crucial ultra-thin dielectric layer. And when we say ultra-thin, we mean it. The patent mentions 1 to 4 nanometers.
Nanometers. I always need a reminder of how small that is.
It's incredibly small. Like a human hair is maybe 80,000 nanometers wide. So this layer is almost unimaginably thin. It's often made of things like silicon oxide or aluminum oxide. Its thinness is key for that tunneling effect we talked about earlier.
Okay, the super thin tunneling layer, what's next?
On top of that, there's a passivation layer. You can think of passivation as smoothing things out, fixing tiny defects on the surface.
Why is that important?
Because surface defects can act like traps for electrons, causing that recombination, that loss we want to avoid. So this layer helps keep the surface electronically quiet and smooth, letting electrons flow better.
Makes sense. Smooth highway, fewer potholes.
Good analogy. Then, formed on this passivation layer, you have the first electrode. This is the metal contact that actually collects the electricity and sends it out of the cell.
Right, the exit ramp for the electrons.
Exactly. Now, here's where this particular patent gets really clever. It introduces specific types of metallic crystals right into this structure on the passivation layer.
Metallic crystals, like tiny metal chunks.
Sort of, yes.
Yeah.
The patent talks about first metallic crystals and second metallic crystals. They're formed on the passivation layer. But the key design feature, the real innovation here, is how the first metallic crystal is positioned.
Okay, how so?
One end of this first metallic crystal sits directly against that ultra-thin dielectric layer. It makes direct contact. And the other end connects directly to that first electrode, the exit ramp.
Ah, so it creates a direct bridge. From right beside the tunneling layer, straight to the electrode.
Precisely. It's like building a dedicated express lane or a shortcut. Instead of electrons maybe having to wander through the passivation layer to find the electrode, this crystal provides a direct, low-resistance path.
That seems smart. Does it mention how many of these express lanes there are?
It does talk about the ratio. It says the proportion of these first metallic crystals, the direct contact ones, compared to the total amount of metallic crystals in that region can be really high, like 50% up to even 99%.
Wow, so they're really emphasizing this direct connection. It's not just a few scattered crystals, it's the dominant structure there.
Yeah, exactly. The design deliberately maximizes these direct pathways.
Okay, so we've got this intricate sandwich, substrate, ultra-thin layer, passivation layer with these special metallic crystals forming direct bridges to the electrode. What are the claimed benefits? What does this structure actually improve?
Well, the main goal, as stated in the patent, is to accelerate carrier transmission through that passivation layer. By providing these direct crystal pathways, it shortens the time required for carriers to pass.
Faster travel time for the electrons.
Right. Less chance for them to get lost or delayed. It also aims for excellent electrical contact performance, basically. A really good low-resistance connection between the electrode and the active parts of the cell.
Which means less power lost at that connection point.
Exactly. And importantly, it helps reduce problems like metal recombination right at those contact points. Sometimes the metal itself can cause electrons to recombine, but this structure seems designed to minimize that.
And does it help protect that very delicate ultra-thin layer?
Yes, that's mentioned too. The design helps prevent damage to the ultra-thin dielectric layer, which is vital for the whole Todicon concept to work reliably long-term. And all of this contributes to improving the open circuit voltage.
Open circuit voltage. Remind me why that's important.
Think of it as the maximum voltage the cell can produce when sunlight hits it, even before you connect it to anything. It's a key indicator of the cell's potential power output. Higher open circuit voltage generally leads to higher overall efficiency.
Got it. So all these microscopic structural changes, the direct crystal bridges, the careful layering, they all add up to squeezing more electricity out of the same sunlight.
That's the ultimate goal, yes,
Yeah.
improving the overall cell efficiency, making the Topicon cell even better than it already is.
So, okay, this is fascinating, digging into the tiny details, but let's zoom out. What does this all mean for us, for the listeners, for the bigger picture of energy? Why should we care about these nanometers and crystals?
Well, connecting it back, these kinds of incremental improvements are actually incredibly important for solar energy's future. Higher efficiency is kind of the holy grail.
Why is that?
Think about it. If each panel produces more power, you need fewer panels or less land area to generate the same amount of electricity. That makes solar cheaper and more practical in more places.
Right. Especially for like rooftop solar where space is limited, or huge solar farms where land cost is a factor.
Exactly. Even a small percentage gain in efficiency, when scaled up across millions of panels produced by a company like LONGi, has a massive impact on cost effectiveness and deployment speed. It helps solar compete better with traditional energy sources.
So it's these small steps that collectively drive the bigger shift.
Absolutely. This patent is a perfect example of that relentless behind-the-scenes innovation. It's not always about discovering a completely new material, but about cleverly engineering the structures we already have, optimizing every interface, every pathway down to the nanoscale.
It shows how companies like LONGi are constantly refining, pushing the existing tech.
Yes, and that continuous improvement is vital. It impacts grid planning, energy policy, even household budgets if it makes solar more affordable. These technical steps directly contribute to making sustainable energy more viable globally.
And for someone listening, understanding this provides a better appreciation.
I think so. It gives you a much deeper appreciation for the sheer ingenuity involved. It's easy to just see a solar panel, but understanding the layers of physics, material science, and precision engineering that go into making it incrementally better, it's pretty amazing. It moves you beyond just solar is good to, wow, look at the incredible science making it happen.
Okay, so summing up our deep dive today, we've looked closely at a patent application from LONGi Solar.
A major player.
And we've seen how they're innovating within the already high-performing Topicon solar cell technology.
Using it really highlights that the future of clean energy isn't just about the big headlines. It's also built on this foundation of persistent, microscopic innovation. These tiny tweaks, like arranging crystals just so they add up.
They cumulatively push us towards that more sustainable future.
Definitely.
So here's a thought to leave you with. As you go about your day, maybe think about the hidden innovations all around us. What other subtle, maybe almost invisible advancements are quietly shaping our world, making things work just that little bit better, pushing us forward in ways we don't even realize.
A lot to think about there.
That's all for this deep dive. Thanks for joining us.
Thanks, everyone.